So today I wanted to speak about how we can prove the strong equivalence principle with local group cluster and stellar strings. And why exactly that? Because the strong equivalence principle is not only one of the pillars of Newtonian, but it is a pillar of general relativity and Newton dynamics in general. So what is the strong equivalence principle? The strong equivalence principle tells you that the outcome of any local experiments in a free-falling laboratory is independent of the locations on the velocity of the laboratory in space-time. What it is meaning is that if I'm throwing an apple in the air, it's going to throw back on Earth at exactly the same speed or under the same acceleration, regardless of the location of Earth, if you neglect obviously the tides effect. So this means that whether the Earth is located in the center of the galaxy, at the current position, or it's completely isolated in the middle of the universe, if I throw an apple in the air, it will always go back on Earth at the same speed. In MOND, it is slightly different. Why? Because the amount of boost that is produced by MOND is given by the total amount of accelerations. So when you have a two-body core, which is the case in that cases, for example, you will have the boost which is produced by the amount of the Newtonian acceleration produced by the object, and the amount of acceleration produced by the external acceleration, in that case is the galaxy. And that's really easy to understand. Let's consider that we have a dust of grain of the same size of the Earth, of the same density as Earth, sorry, which, if I didn't make any mistake, corresponds to a dust grain of around 0.05 millimeter. Okay, so in that case, it's very likely that there will not be any water, so it will be great. And so in that cases, what tells us MOND and dynamic is that if the object is isolated or far enough so that the external acceleration is extremely low, you're going to find the classical Newtonian dynamic. So if I throw an apple in the air, it will go faster than wonders. If now I put the Earth in the center of the galaxy, or even at the solar, or the dust of grain, sorry, as a solar neighbor, you will see that basically your external field acceleration is in the Newtonian dynamic, so the amount of boost is also equivalent to something in Newtonian dynamics, so you recover the classical Newtonian dynamic, so the apple will fall exactly as on Earth. Now, if the dust of grain is around the solar neighborhood where the external acceleration is of the order of a naught, you will find something which is called the quasi-Newtonian dynamic, and it's equivalent to the Newtonian dynamic, but with a renormalization of the gravitational acceleration, dependent on the value of the external acceleration. So the conclusion is that in MOND, the result of an experiment depends on the location of the space. It's completely different than what you have in classical Newtonian dynamics, and so you break the strong equivalence principle, and this is usually what we call the external field effect. So it's already been shown a lot that the external field effect can explain, and it's extremely important to explain the dynamic and the internal dynamic of several galactic objects, such as dwarf galaxies. And you have here the picture that already showed Stacy 2 days ago with the velocity dispersion of dwarf in M31 that are predicted in isolated in green and in wave when you take into account the external field effect in white, and you compare that with the observations. And you see that indeed the external field effect can play an important role, and it's crucial to be explained to explain the observation in M31. This has also been shown with many other dwarf galaxies since, like Quadrant 2 and DF2. But another thing also which is really often neglected is that not only the external acceleration can modify the internal dynamic of the object, but it can also perturb and shape the acceleration or the potential by modifying it. And that's really easy. So here I'm going to take an example of a galaxy inside a galaxy cluster, which was the first example that presented Zufeng Wu in 2010. And so for that, it's really easy. So let's assume that you have a galaxy, which is here represented by a constant density distributions that is under an external acceleration, which is produced by the galaxy cluster. So you have the amount of total acceleration, which is equal along the galaxy, because for simplification, let's assume that the acceleration is constant across the galaxy. So at 2 points that are separated at the same distances from the center, you have the external acceleration that are under that way, so the galaxy cluster is in that sense. You have the equivalence of the internal Newtonian acceleration produced by the object itself. And so here is the total Newtonian acceleration that you have at the end, gravitational accelerations, where you can see that you have the amount of acceleration here, which is smaller in terms of norm, than in the other side. And so what it is meaning is that in MOND, the boost is going to be more important in that direction than in that direction, which if you go towards the potential, you will see that you have something which is exactly under that shape. And what you can clearly see is that at the end you have something with an egg shape, with the top of the eggs, which is always pointing towards the source of the external accelerations. And that's something which is not predicted in Newtonian dynamics because it's something that is a consequence of the break of the strong equivalent principle. Another way to see that is that if you go in the human formalism, you can write the Poisson equation under that way, where you have the classical two parts, the Newtonian bionic distributions, so it's the classical Poisson equations, and here you have another term, which is the phantom dark matter. So it's a mathematical ansatz of dark matter. So it's not something really physical, but it's the mathematical equivalent of the amount of dark matter that you will need to add to reproduce the MOND accelerations. And so in that cases, in that specific condition, you can have some lobe of negative dark matter, which are indicated here by the dashed line. And so the negative dark matter, again, remember, it's not something physical. What is negative matter in general? It's a repulsive forces that is going to compress the potential that you have here. And so that's why you finish with something which is more compressed. So you can say, okay, right, great. We have a way to maybe try to see if we can observe the external accelerations and or to break the strong equivalent principle. So, okay, galaxy and galaxy cluster are really great because you can see that, or wherever the problem of galaxy cluster, is that all the phenomena can also explain this asymmetry, such as, for example, the Coulomb pressure stripping, because galaxies tend to be gas-rich, and so you can also have a motion, a ramp pressure stripping which is induced by the motion of the galaxy in the galaxy cluster, which is going to push the gas away. So it will be extremely hard actually to differentiate the flattening or the lopsidedness of the potential which is generated by the external field effect and compare it to something which is due to the ramp pressure stripping or star formation, evolution, and so on. And so that's why for ages now, for years, I'm pretty convinced that globular clusters are in general better tracers of the external field effect because the exact same effect is also present in globular clusters because globular clusters tend to orbit around some satellites, like in the Milky Way, and there are many advantages. First of all, the majority of them have absolutely no gas or really a few amount of gas, so you can already neglect the ramp pressure stripping, and for most of them they're also old enough so that they are varialized, and most of them also in the Milky Way orbit in the halo where the external field effect is at the maximum of its peak. So globular clusters are a better tracer of the external field effect than a galaxy cluster. I think if we really want to see if we can break or not the strong equivalent principle by seeing the morphology and see if indeed a globular cluster is lopsided or in other sense has the shape of an egg. Or wherever globular clusters suffer from other things, globular clusters can be destroyed by tides and can form stellar streams. So stellar streams are formed by the disruption of a globular cluster or about galaxies around a galaxy like the Milky Way. And you can see that at the end, so the particle leaves the Lagrange point and creates a really long extending stellar streams, as you can see here. So around the Milky Way right now, we know roughly around 50 known stellar streams around the Milky Way. Most of them have been discovered really recently thanks to Gaia. And only 9 of them are with surviving progenitors. And now I'm going to explain you why it's important that we detect also the surviving progenitors. So, here you have a map of the stellar streams in the Milky Way around 25 kiloparsec. And you can see really clearly here the structures made by the Sagittarius stellar stream, which is the most massive stellar streams present around the Milky Way, but it's formed by the disruption of dwarf satellites. Another one that you can see is that you have a lot of other kind of structures that are really hard to identify, except one which is called the Palomar 5, which clearly standard, it's clearly visible. And actually, if you zoom it, you see that it's clearly visible compared to the background. It is normal, this is a string with the highest contrast towards the background, even higher than the Sagittarius one. And so what you can clearly see on this picture is that not only the Palomar 5 is really bright, but it's also asymmetric. You see that the leading tail here is shorter than the trailing arm by a factor of 2 almost. And that's really interesting because when you do simulation of these stellar streams, in Newtonian dynamics, which is indicated in red here, you see that the lengths of the arm are predicted to be almost symmetric, which is in general normal what you see in Newton Obviously, that's dependent on the orbit of the cluster, but for Palomar 5, in that case, you expect to get something which is completely symmetric. Whereas, when you do the exact same simulation with the same progenitors in MOND, you see that the stellar stream is asymmetric with exactly the same orders as seen in the observations. So, in conclusion, in MOND, you can see that stellar stream can be asymmetric, which is not the case in Newton, at least for the stellar streams. And so the reason behind this is again due to the X shape of the potential, where in Newton you have something which is symmetric, and in the counterpart in MOND you have something with an X shape, again with the top of the X which is pointed towards the Milky Way, so in that case it should be around that direction. However, in lambda CDM or in Newtonian dynamics, it's always possible to explain that you have an asymmetry on the stellar streams due to external perturbers. Some of them that might be due to dark matter halo flyby. They're going to kick the stars out of the streams, making that you will get something asymmetric here. However, the probability is really low. I mean, measure, basically you expect maybe one interaction maximum with a dark matter halo. You can get GMCs. Again, they're going to kick the stars out in the leading arm. However, this, for the moment, we still not have found any giant molecular cloud that can explain this asymmetry. And then another one is the galactic bar. So the same effect should also be present in MOND potentially. And the galactic bar can also generate an asymmetry. However, and that's something that will be published pretty soon, thanks to Gaia measurements of the proper motions, now we can see that the pericenter of Palomar 5 is never close enough of the disk so that the bar can interact, regardless of the mass of the pattern speed of the bar. So actually, we can already remove this conclusion. So it's still possible that you have dark matter halo in lambda CD or whatever, but I think the easiest conclusion for the moment is that something in MOND or in something brainstorming in principle and explains this asymmetry. So the problem is that it's just one stream, so we need to see this in most streams to see that it is, if the observed stellar streams are also asymmetric, as predicted by MOND. The problem is, as I was saying before, only 9 stellar streams are with non-progenitors, and here you have the map of the stellar streams and the different track found by the different authors. And as you can see, except for Palomar 5, where most of the people agree on the position, the distance, we have still some debates. You can see for the other streams, even in the position, nobody agrees exactly to what is the stream, what is the extent of the streams. And it's extremely, and it's normal because it's really hard to know where is the end of the streams, where is the beginning of the streams. So not only you have to get the progenitor to be able to get the length of the leading or the trailing arm, but also you have to know where finishes stellar streams. And you can see that for all of the others, it's impossible to see where is starting, where is beginning another one, because we are still debating on that, and it's just recent discovery. So we still have to do a lot of work on the observational side to better characterize the observed stellar streams. So that's the problem. For the moment, we don't have another stream in which we can really do these studies. Hopefully, Gaia make a very big breakthrough in the recent years with an open cluster stellar streams called IADES, because so IADES is the closest open cluster from Earth, and it's been observed that it has the stellar streams around 800 parsec long, as you can observe here, detected by Gaia. And what you can clearly see in the stream is that you have an asymmetry, but in that case it's the leading arm which is more populated than the trailing arm, and Pavel measures this asymmetry number and measures that an asymmetry of the ratio around 2.5. Typically you have 2.5 more stars in that direction here in the area indicated in blue, that in the counterpart in the trailing arm. It is something extremely interesting because in MOND, in that cases, it's exactly what you predict. As you can see, when you compare in Newton, you expect something more or less symmetric, whereas in MOND, you have an over-density which is predicted in the leading arm of the streams, as you can see here. And now if you measure the amount of asymmetry that you will expect, you can see that in MOND, depending on the mass of the progenitors, or of the cluster, which again is normal because that will generate the amount of boost that you need, so the amount of asymmetry that you can generate at the end. You can see that you can get an asymmetry which is clearly visible in MOND in almost all the masses, whereas in Newton you get something around 1 or even slightly below 1, so with a trailing arm which is slightly more populated in that cases. And you can see that it's exactly what you see in MOND. or wherever the value maximum that you reach is around 1.2, whereas when you compare the observations, you have something around around 2.5, so you see that you have several sigma of differences anyway. And the problem is, I think in that case the problem is not on the simulation side, it's in the observational side. Because the selection that I was showing you before with these stars here selected in Gaia, actually around 20% of them are contaminants. And that's clearly showing up because here we selected the stars and we used the Gaia radial velocities to see if indeed it was following the stellar streams. And also naively you will expect that they'll follow here one of the two lines, either the blue or the green line, really well like this. And you can see that a lot of stars are actually completely outside at several tens of kilometers per second of differences compared to what you will expect. So actually in that selection you have a lot of them that are contaminants, and especially in the training arm you see that the one here start to be contaminated really quickly, I think shorter than in the leading arm, which might also explain a part of these distributions. The other thing is also that we have been seeing that the presence of the galactic bar can not only, so we thought initially it can generate an asymmetry, it's not the case. What makes the bar is actually change the track of the streams. So here you have the model made with two in Newtonian dynamic. With two different types of models, the green one without a bar, the blue one, sorry, without a bar, and the green one with the presence of a bar. So, and what you can see is that in that cases, the track of the stream is completely different. And so if you base the selections based on one of the models or the others, in the new selection that we have, in the absence of a bar, we find an asymmetry around 1.4, with again a leading arm which is slightly more populated, whereas if you have a fast bar or a rotating bar, you get something around 1.1. And just to remember that the asymmetry that we found for the ILS in MOND is around 1.2. So in both cases, either with the absence of a bar, so when you remove the contaminants, or when you include also the bar, you can see an asymmetry which is more consistent with what we see in MOND. But just to a quote, we found also in the simulation that the simulation tend to be also slightly asymmetric with a leading arm which is also slightly more populated, more around 1.07. 1.10, so it might also be able to explain partly some of this. However, also in our new selection, there is likely also plenty of contaminants, so we have to do some follow-up, but I will be really happy to speak about that later. So future perspective for the fields, so the external field effect can generate an egg-shaped potential of the globular clusters. It's not always true. Depend on the mass of the globular cluster, depend on its locations in the galaxy, and it depends of its size, so basically of its density. And here we have just an example of the amount of phantom dark matter that you have for all the globular clusters as the M31 galaxies. And here we have the equivalent effective potentials. And what you can see is that you can split them basically in three different types. The spheroidal potential, which are the one either too massive or too much nearby the M31 so that the external field effect is almost negligible. You have the elliptical that are too far away or are almost isolated. And you have the ovoidals, which are the globular clusters of the good masses in the good range of distances, so typically between 15 to 80 kiloparsec compared to the center of M31. And so, first of all, two things, two perspectives. One is observational. You have to detect and to quantify the degree of subtleness of the globular clusters in the local group. Because again, in MOND, you don't expect to get the asymmetry in all the globular clusters. So you have to do that for a very large amount of them. Also, on the theoretical side, you have to do the prediction for each globular clusters to see what is the degree of lopsidedness that you expect. So on observational side, how can you quantify this? Well, we have to go in to see our colleagues that do ornithology that study the shape of the eggs of different birds. And actually, they get a really good parameter, which is the pointedness and elongations, which tell you how pointed or egg-shaped lights is an egg. And this is a different type of species of eggs, of birds, sorry, that get different shape of eggs. So they use mathematics behind to define the morphology. And you can actually fit this on the isochrone or isopotentials to quantify the amount of lopsidedness of the globular cluster that you can observe. And the problem now is to observe the outer part of the globular clusters, because you expect the external field effects on the shape of an X to be more important in the outer part of the globular clusters. And this is clearly visible on a quick simulation. So I took the most pointed clusters that I had, that I showed you before. I did some simulations of it, and you can clearly see it's pointed towards that direction. So M31 is towards that direction. And I apply the formulation mentioned in the other paper, and I just measure what is the evolution of the parameter A, which tells you the lopsidedness. So 0 corresponds to something spherical or elliptical, and something above 0 will tell you that you have something asymmetric with the trailing, the leading part here, which is more compact than the trailing one. And what you can see is that while in the center, Newton do something pretty weird, but I think it's a problem that I identified to solve. But otherwise, you see that in red, which is the MOND simulations, you see that you will start to get a deviation around the given distances, and then you start to increase the amount of lopsidedness. But it is normal because in the inner part you are in the Newtonian dynamic, and so only when you start to depart from the Newtonian dynamics that you're going to see these evolutions. Whereas Newton, you see something which is always around 0. So I think now we have the process to be able to apply that to the observations, but still the problem is how can you really observe the outer part of the globular clusters, because it's really challenging. And so for that, there is two different ways. In the Milky Way, we need to remove all the contaminants. We need to select all the stars, remove all the contaminants, because we are speaking to select maybe maximum 100 stars in the outer part of the globular clusters to see the shape of the morphology of the shape. So for that, we have to use spectroscopic data, because Gaia data alone are not able to properly select the stars of the globular clusters. We really need to be able to get the amount of chemistry, metallicity, and alpha abundances to select the stars that belong really to globular clusters. And part of it would be possible with the WIV and foremost instrument. Not only the surveys, but the instruments, at least for WIV, will be able to apply on it. And the WIV surveys in general, or instrument, will be available in this fall. And in the next decade, that will be possible with 10-meter class telescope, which are debated to be constructed, either the Wide Spectroscopic Telescope or the Mauna Kea Spectroscopic Explorer, which will be extremely great if we can construct them. And the advantage also of the spectroscopic selection is that we can also get better constraints in stellar streams, thanks, to model them and so on. And in the local group and in the local volume, another instrument will be actually useful to do large statistics, not only on a few globular clusters, but on a wide variety of globular clusters, thanks to the Euclid missions, because by using integrated light photometry, we can go up to 20 megaparsecs, and we can study the morphology of the external part of globular clusters with these really nice missions that will be launched really soon. And I let you with the conclusions that are writing here. And just the big conclusion is that we have still many work, both on the observational side, to detect the globular clusters and to quantify the morphology of the globular clusters, but also on the modeling side, either for the globular clusters or on the stellar stream as well. Thank you.
Thank you for the nice presentation.
Okay, yes. Thank you very much. It was very nice. Well, I was wondering if for the bar interaction, you have taken into account the possible resonance with the orbit, because that will be more effect, and then you can also have effect of spirals, which are less intense, but if they resonate, there can be more perturbations.
Yes, so that is taken into account, because that's purely numerical simulations with perfect bar potential inside, so you take into account the resonance by default. And also with the mechanism that you have behind, we can also include some bars by adding some different modes. So that's something that we would like to study now, because actually in the part of the ISS, it's possible that the bar are even higher impact than the bar itself due to these locations. So that's something that we need to study. So this was just an exploratory mode. So there's many things that we can tweak, just the length of the bar analysis. But it's really interesting to see that we are not able first to predict an asymmetry, as was seen for Palomar 5, for example, with simulations, but also that you see that you have modification of the track by itself. So that was the first thing, and then we based the new selections on these different models, and so we have two different competitive selections, and even with the metallicity alone, we are not able to separate them together. For the chemistry alone, we are not able to say which selection is the best. So that's why we need also to get additional follow-up.
Just a quick question. So the theory tells you what the potential, let's say, equipotentials look like, but how did you deduce it from the stellar distribution? You assume that, like, isophones follow potential?
Yeah, so actually that was a big question that we had initially, that we weren't sure it was the case. So that's why we did the prediction with really naive analytical formulations. We did the n-body simulation with the phantom references to see if the isophote was following the isopotential. In that cases, it seemed that in all the cases it was following more or less the isopotential. So maybe you have differences, but for a really long time we didn't have the formalism, and it's only a few years ago, actually during COVID, that I found that there was this paper of the egg shape of the birds, which I think is really interesting in that case because not only you can see the asymmetry, but you can quantify it. And now we have to redo all the process by studying the different simulations, study the potential, and to see if indeed you have the same lopsidedness. But I think this is one part of the job. It's really on the theoretical side on MOND to see what is the prediction that you can do in MOND. You can also just use that on the observation and see if globular clusters are symmetric or not, which is completely agnostic in that cases, just to see if is a strong equivalence principle respected or not. And that's something which is extremely interesting because it's completely agnostic. You don't have to be in a Mondian behavior or Newtonian behavior. You just see the observation and you see if it is asymmetric. Then you can discuss with tidal effects and like that. But for most of them, you know that you will not be affected by tidal effects. So the lopsidedness can just be explained by the break of the strong equivalence principle, which I think is a really nice step to do.
So I was wondering, earlier in your talk you had the simulation of the Palomar 5 stream, the Newtonian prediction and the MOND prediction. So I was just wondering, what's like a brief summary of what you did for that simulation? Did you use a particular code?
Yeah. So for the simulations, basically it was modeled with the King profile. So we did several tests of the potential and so on. Both of them was modeled, so Newton with Francis in MOND part with the phantom references. And so the advantage of that is that you can use exactly the same grid of the simulation with the same limitations, same behaviors. So you can remove all, let's say, the numerical effects. And it was a big challenge because when we saw the asymmetry in the first time, we were, okay, there is something wrong with the numerical code because due to grid effect, it can also generate potentially such asymmetry. And actually then we derived the analytical formulation and then we saw that, yeah, actually, globular clusters tend to be avoidals, and that explains naturally the asymmetry.
Thank you.
Thanks. So I think your argument about the external field in MOND could change the shape is convincing. So I'm just wondering, in Newton, because you assume the external field across global clusters is constant, which is mostly okay for MOND. So if in Newtonian gravity, a constant external field would not cause any X shape, as you described, but there could be a small difference in the external field at the near side or far side, which would also be able to cause the X shape. So have we ever done these calculations yet?
So I think we need to do really, in that case, simulation also in Newton with the acceleration. But again, the size of the globular clusters is here, the first size is around 0.4 kiloparsec, which to the sides of the distances here that are separated from between 50 to 200 kiloparsec is negligible. So the variation is likely negligible, but in any cases, that's why we really need to be able to quantify the amount of lopsidedness. So without the formalism that we had to quantify it, it was impossible to do so. And it's only now that we can do that we need to go in Newtonian simulations also to see what is the amount of asymmetry that you expect due to exactly the difference of the external field effect, external acceleration along the cluster. So that's something also that we need.
Yeah, I understand the size is small, so but the shape, deviating from the sphere shape is also small. So by naive thinking, I cannot exclude this possibility.
Yeah, exactly. I completely agree with you. So that's why we need to do the study. My bet is that it will be really negligible. But that's something that we need to do. Yeah.
Okay.
So it's easy for me to imagine how the egg shape is established in MOND by the vector of the external field. But of course, these things are all orbiting around all the time, so it's not a static case. Can you see in the simulations that the position angle keeps up, i.e. is the time scale short enough in the clusters that you,
Actually, yes. So we did some simulation with different eccentricity of the orbit. And we find that with a reasonable eccentricity, except when you start to be totally disruptive, you get always the same shape. It's almost negligible. But this was at the time with an high identification because we didn't add any mathematical formalism to quantify this. And it was really made at the end of the thesis also. Now we have the formalism, so I would like to really to re-explore that things. But again, I think there is two parts. There is the simulation part, and I think this is really the things to do to see the globular cluster of reality and to do that with different asymmetry and eccentricities of the orbit to see if it's exactly the same or if you still have some tiny variations, especially on the outer part of the globular clusters, where
it might be interesting to do this too for some toroidals, which are basically really diffuse globular clusters, and there may be a time scale where there's a distinction.
Well, so we did that for Sagittarius. And for Sagittarius, for example, you don't expect something, but it's a really massive one. So yeah, but my bet will be that we will get more or less the same for the classical, and maybe just in the outer parts of the dwarf galaxies, you can really detect it. And it's really interesting because right now we're just starting to see the halo of the dwarf galaxies, where you expect that you will get all this asymmetry and so on, but the problem is that in that case you are also affected by tidal effects. So it seems that we are still just right now starting to discover stars in the halo of the dwarf. Yeah.
If the object is far away, it makes you weird. The line of sight is more or less parallel to the external field.
Yes.
So you expect to see nothing.
Yeah. Yeah, also, no, exactly. Yeah. So that's why I was saying it's really depending on your locations where you are inside. At some point, we are too far away to be affected by the external field effects. And that's the problem. That's really to get to quantify this.
One more question.
Thank you.
Hi Thomas. Thanks very much for also highlighting Shiven's work, which was actually down here in the Canarias early in your talk. I actually had to missed a little bit what you said in between. I'm very sorry about that. But I want to make one perhaps a comment is it's good to do these tests in systems not in or not satellite galaxies, where there are competing dark matter or competing alternative gravity theory, for example, which I was on a paper on about the chameleon effect, which can also produce a symmetry due to the dark matter associated with the dwarfs. Having a chameleon force. Okay. Okay, so you want to avoid, actually you want to do cleaner systems.
Yes.
That's what I meant. So star cluster is great. And I would go even further to say, could we think about gas clouds? Because they are more available and we can use radio and other observations to tell us about the morphology. And I believe there's plenty of evidence of asymmetric gas distributions. But how do you distinguish what is real from, what is gravitational, what is impact and other induced asymmetric ground pressure? You have to play with that. I believe, but if with this eye, at least it's a clean system.
So I think in the Milky Way we can neglect the ground pressure for the globular clusters in general.
No, I'm saying, sorry, I said to myself about the gas clouds themselves.
So that's why
the symmetry of a disrupted cloud.
Yeah, so that's why it will be extremely difficult, because in that case you need also to take into account the hydrodynamic forces and so on, which can be complex to model or to understand.
Mm.
So that's why I think
But
it's better to just go into particle to engineering in that cases.
External field is different from the RAM direction, hence you
If you
have
know
a handle of it.
If you know the orbits, and that's the problem now, so to know the orbit of these things.
Circular?
Yeah.